Good afternoon, everyone. Good afternoon, everyone. I am Chanda Devnath, one of the PMRF fellows. So, in this classes, I usually discuss about the retrosynthesis in organic chemistry. So, mainly in this doubt clearing classes, here I usually discuss about some important name reactions and reactions mechanism which may help you to predict the retrosynthesis of a compound and also clear your doubts like how just by seeing the product or a compound how can we predict the retrosynthesis of that compound. Moreover, moreover if you are planning a reaction, like if somewhere the name reactions is given, the reaction, what is the mechanism behind this reaction, that I will discuss in this class. So let's start. In the previous classes, I have discussed about different type of name reactions as well as carbon-carbon double bond formation reactions, different type of oxidation reactions, followed by different type of reduction reactions. In the last class, maybe I have discussed about the different type of rearrangements, the like important ones. So if you are interested to know about those, the video has been uploaded. You can go and check from there, and also the slides are there in the Google Drive, from where you can get access of that. Let's start. So today I will discuss about different type of substitution reactions. So we know about SN1 and SN2. I will just give a overview because we know about that. Then we'll solve the question based on that. Then based on this substitution reaction, there are some two famous name reaction, that is Apple reaction. Next one is Mitsunobu reaction. So first we will discuss about this type of substitution, that is SN1 and SN2. I am not going in a deep concept for these two because they are very known to all of you, I guess. So what is nucleophilic substitution? Electron-rich nucleophile selectively binds or attacks the positive or partially positive charge of an atom or group of atoms to replace a leaving group. So in substitution reaction, what we do? Suppose we have a electron-rich nucleophile, like whatever is coming, that should be electron-rich nucleophile. Like here the nucleophile is this pH S-. Negative charge denotes that it has a high density of electron. It attacks to a positive or partially positive charge. This is positive and this is partially positive, like the leaving group has not lived yet. So this is not a totally positively charged, but it has, due to this minus I effect of this chlorine minus, it has a delta positive charge, like partial positive charge, because the electron cloud is shifted towards the chlorine center. The electron cloud is shifted towards the chlorine center due to its minus I effect. Due to that, there is a scarcity of electron at this carbon center, so it's a partial positive charge. Then the nucleophile will attack to this partial positive charge center or a totally positive charge center and give a compound where the leaving group has been substituted by the nucleophile. See, there is no leaving group is there, whereas the leaving group is substituted by this nucleophile. That is called nucleophilic substitution. Now there are two types. One is SN1, the another is SN2. What is SN1? SN1 is a unimolecular reaction, stepwise carbocation generated, and it depends on in this order. What is I am saying by this 4 line? In case of SN1, as I show in this reaction, like first in this the living group left from the system creating a total positive charge and the nucleophile enters, whereas in this case the living group is still there but it's shifting the electronic cloud towards itself and the nucleophile attacks to the center and the living group leaves from the system simultaneously. But in case of SN1, what is happening? The first one. In case of SN1, first the living group will leave from the system creating a positive charge carbon center, and then the nucleophile will attack to this positive center giving us this substituted product. It is unimolecular. Why? Because here the first step is the rate determining step, and in this rate determining step only one compound gets involved. Only because here the living group is just leaving, so only one component is getting involved. Whereas the rate will be depending on the substrate only. There, because of that, it is unimolecular reaction, and the reaction rate varies like that. The 3 degree will react faster than 2 degree than 1 degree. Why? Because if it is 3 degree, then this positive charge is more stable. As you know about the carbocation, I am not going, you know that 3 degree carbocation are more stable because of hyperconjugation and inductive effect of the methyl groups. So the 3 degree carbocation are more stable carbocations. Because of that, this carbocation will be more stable, making this slow step faster, making this slow step comparatively faster. Therefore, the 3 degree carbocation will react faster, whereas 2 degree, then after that 1 degree. But in case of SN2, what is happening? This is a bimolecular reaction. We have discussed the second one, where the living group does not leave from the system totally. It's still there, but it's just shifting the electron cloud towards itself. Because of that, the nucleophile enters and attack to that carbon center and kick out the living group from the system. So here a Walden inversion is happening. Suppose, imagine like this is also called an umbrella effect. Imagine that this is the umbrella. This is the umbrella upper part, and this is the stick. Okay. Now suppose your another stick is there and you are pushing from this side, or wind is coming from this side. Suppose wind is coming from this side. What will happen? This will totally reverse and wind will come here. The wind is actually the nucleophile. So when the nucleophile attacks and the living group leaves from the system, there is an inversion of the carbon center. So whatever stereochemistry will be the carbons after entering the nucleophile, the stereochemistry will be totally reversed. But in case of SN1, the stereochemistry will be same, because here the carbocation will generate, and we know the carbocation is a planar system. Carbocation is a planar system, and planar system are available to get attacked from above and below both of the side, because this is planar. This is just in the plane. Suppose this is like a paper. It's like a paper. So the nucleophile can come from this side as well as this side in a similar way. So there will be a 50-50. The formation will be 50-50, and when it is 50-50 means this totally stereochemistry can't be determined. 50% of upper attack, 50% of lower attack. But here in this case, selectively there will be a opposite whatever the living is, the attack will be from the opposite side of the living group. Okay, there will be no 50-50. What is the rate of the reaction? It depends, like 1 degree will react faster than 2 degree than 3 degree. Why? The 1 degree is less sterically hindered. So if something is less sterically hindered, you can attack that part very easily. Suppose something is blocked by a wall, a huge wall. Anything can't attack that place easily. But if it is blocked by some small walls, it's not covered by some big walls but some small walls, then anyone can attack to that place quite easily. So 1 degree will react faster because it can be attacked by the nucleophile easily. So just to clear your concept, I have given this question. What is the correct order? It has been come in different competitive exam also, maybe this question, some previous year NET I think. So you know that just by understanding the concept you can attend those questions. The correct order of reactivity of the given bromides in SN1 reaction. So among these three, which one will react faster in SN1 reaction and which one will react slower in this, among this you have to determine. So we know in case of SN1, wherever the carbocation, generated carbocation is more stable, that will react faster, because in case of SN1, first the leaving group will leave, first this bromine one will leave, and wherever the after leaving of the leaving group, if the carbocation is stable, then that will react faster. So let's generate the carbocation first. So here the carbocation has this double bond stability. This has also this double bond stability. This has also the same. So we cannot determine from this conjugation stability, because if we just there is only one pi bond stability, and but this we can't determine between these two, right? So just based on the conjugation stability we can determine which one will be more stable carbocation. So we have to focus on the another concept, that is aromaticity. I think you know about this, that is aromaticity. A system, a conjugated system, completely conjugated cyclic system, completely conjugated, Hooke's 3 law, the system should be conjugated, the system should be cyclic, and the system should have 4n plus 2 pi electron. Then that is called aromatic. So all these systems are cyclic. So Hooke's first law is clicked. Then the second is the system should be conjugated. So here the system is conjugated, but the number of pi electron. How many pi electron? There is 2 pi electron. Here 4 pi electron. And here 6 pi electron. So here this 2 pi electron, is this following Hooke's law? Yes. If 4n plus in 4n plus 2 pi electron rule, if n equal to 0, it will have 2 pi electron. But here this is not possible. This is not following the Hooke's rule. Here if n equal to 1, it will give 6 pi electron. So obviously these two will be more stable than that of the, so the least stable will be 2. So the least stable will be 2. Now which one will be more stable carbocation between 1 and 3? Now see, in case of 3 there is a cyclic conjugation. This goes here, then this goes here. So there is a possibility of long range conjugation. This goes here. There is a possibility of long conjugation, whereas there is only one type of one single conjugation. So obviously then it will be 1, then 3. Okay. Now you have understood SN1, SN2. Now we will try to solve some name reaction based on this SN1. I just discussed about this SN1, SN2 because to give a recall what is SN1, SN2 and how the stereochemistry matters in case of SN1, SN2. Next, go to some name reaction. These name reactions I think you are getting again and again in your assignment. So by solving this you will get a broader idea which may help you to understand the questions and also help you to solve or select the correct option. So next, first is apple reaction. So what is apple reaction? Apple reaction is an organic reaction that converts an alcohol into an alkyl chloride. So what is they are saying? If you have an alcohol, then we have to substitute that alcohol with any halogen like chloride. Then we can perform this apple reaction. So what are the reagent we use in case of apple reaction? First is PPS3, that is diphenyl phosphine, and next is carbon tetrachloride, that is CCl4. So the use of carbon tetrabromide or bromine as halide source will yield as alkyl bromide, whereas if we use carbon tetraiodide or methyl iodide or iodine, it will give us alkyl iodide. So this process can be applied not only for preparation of alkyl chloride, for preparing other alkyl halides also we can use this process. Now you can see the reaction, what is happening. If you are taking an alcohol and adding PPS3 and CCl4, you will get this alkyl halide. What is the limitation of this reaction? The use of this reaction is becoming less common due to carbon tetrachloride being restricted under Montreal Protocol, because we know that carbon tetrachloride leads to generation of chlorofluorocarbon, so it is a CFC gas, therefore it's a huge effect on our ozone layer. We know about this, so therefore the use is getting decreased day by day. We know about all these things. So what is the mechanism? First, this PPS3 phosphorus will attack the vacant. Phosphorus will give its electron to the vacant d orbital of chlorine. Vacant d orbital of chlorine and cleave this carbon Cl bond, generating PPSCCl and CCl3 minus. This minus will take up the proton from the hydroxy group. After that, this hydroxy group will attack this phosphorus center and removes this chlorine atom. Oxygen phosphorus bond are one of the strongest bond in organic chemistry. Oxygen phosphorus, wherever oxygen gets a phosphorus, it is prone to attack to that phosphorus center. then the chlorine atom will attack again. Now we know that OH group is a bad leaving group. OH group usually is a bad leaving group. So to substitute this OH group is quite difficult because OH group is a bad leaving group, because it will leave the system as a OH minus, that is not stable at all. So it is not prone to leave a system. It is not that much prone to leave any system without any driving force. Now that's why we are to give a driving force. What we are making a bond with phosphorus. Now this oxygen gets a driving force, because if it breaks this bond with the carbon, it can form a bond with the phosphorus, and oxygen is always prone to make bond with phosphorus. So it's getting a driving force. Because of that, the chloride ion, when attack to this carbon center, this carbon oxygen bond breaks very easily, whereas in this case it is very difficult to break because there is no such driving force to remove this OH. But here, due to presence of this PPH3, it gets a driving force and it can be removed from the system and giving us a substituted product. Now if we look into the stereochemistry of this reaction, so what is the substitution type here? Here the substitution is happening. This is just attacking to the carbon center, and if you imagine this is a leaving group, it's leaving. Now this is SN1 or SN2? This is SN1 or SN2? Obviously this is a SN2, because the leaving group does not leave from the system without any attack of the nucleophile. When the nucleophile attacks, then the leaving group will leave from the system. Because of that, it's a SN2 reaction. This is an SN2 type reaction, and we know in case of SN2 type reaction what happens? There is an inversion of configuration. There is an inversion of configuration. Because of that, wherever, like which side, if the OH is, suppose OH is connected to the carbon from above the plane, now the chlorine, after the chlorine attack, it will go to the below the plane, because it will attack from the back side of the substrate or the leaving group. Next we will discuss about Mitsunobu reaction. This is another type of substitution reaction to substitute a bad leaving group, that is OH. To substitute the bad leaving group, that is OH. And previous also, so here, so it is a modification of Appel reaction, because as I said, in case of Appel reaction, what is the drawback of the, or limitation of the reaction? The use of CCl4, because we know CCl4 is a source of CFC gas. Therefore, the use of CCl4 is getting decreased day by day. So scientists came up with a new type of reaction where instead of CCl4 we can use some different reagent. So next is Mitsunobu reaction. This is an organic reaction, and that converts the alcohol into a variety of functional groups such as ester using triphenyl phosphine and an azo dicarboxylate, that is diethyl azo dicarboxylate, or so the alcohol reacts with the phosphine to create a good leaving group, as the previous then undergoes an inversion of stereochemistry in classic SN2 fashion as the nucleophile displaces it. This is similar to the Appel reaction, so it will be easier for you to understand. We have discussed it. Instead of just CCl4, we are using a different reagent, that is diethyl azo dicarboxylate. So a variation of this reaction utilizing nitrogen nucleophile is known as Fukuyama-Mitsunobu. Instead of this acid, if we use any nitrogen center amine or something, this is called Fukuyama-Mitsunobu. So what is the mechanism of this reaction? First, whatever we are doing with CCl4, we will do that the same with diethyl diazo carboxylate. So here this ppH3 will attack to this nitrogen center and open this double bond. After that, this N- will take a proton from this acid, which is acting as a nucleophile, which will be acting as a nucleophile. Then it will form this complex. After that, this O- will attack again to this ppH3 plus, and this will cleave. Now when sorry now our alcohol is there. So now our alcohol is there, we know in like previous one. So our alcohol will attack. They have made complicated in this case. I'm just going to a simple way. Like just compare with the apple reaction. It will attack to this ppH3 plus, forming this same intermediate like 8, which you got in case of apple reaction also. Just try to compare. In case of apple reaction also, this intermediate 7 and here the intermediate 8 are similar, totally similar. Now our the nucleophile will attack to this carbon center and remove this leaving group from the system, generating this product 12, that is ester here. Okay, this is just similar to the apple reaction, but instead of CCl4 we are using diethyl azo-dicarboxylate. So as it is similar to the apple reaction, what will happen? Here the stereochemistry will be reversed, just like in case of apple reaction, because it is SN2 and SN2 always leads to inversion of configuration. Next we will discuss about some reaction leading to the oxidation of double bond. Some reaction leading to the oxidation of double bond. I am trying to mix up the questions so that you can get an idea all the type of name reaction. And I am trying to the important one only. So first in Lemaitre-Johnson oxidation and second is ozonolysis. So what is Lemaitre-Johnson oxidation? The Lemaitre-Johnson or the Malaprade-Lemaitre-Johnson oxidation is a chemical reaction in which an olefin undergoes oxidative cleavage to form two aldehyde or ketone units. The reaction proceeds in two-step manner, beginning with dihydroxylation of the alkene by using osmium tetroxide and the reduced tetroxide, followed by Malaprade reaction to cleave the diol to period by using periodate. This periodate also serves to regenerate the osmium tetroxide, because it is reduced, and osmium tetroxide is very costly reagent, very much costly reagent. So whenever we are using this osmium tetroxide in a reaction, and if we just as it is getting used as a equivalent amount, because after 1 mole reaction this will be reduced from, and it can react further. So if we use a catalytic amount of oxidant like sodium this NaIO4, this will regenerate the osmium tetroxide, and making the use of osmium tetroxide is in a catalytic amount. Otherwise we have to use it as in a stoichiometric amount. So what is the So here you can see the mechanism. If we break, so this OH will attack to this iodine. This will open. Then another attack of OH leads to opening of another, forming the cyclic intermediate. Then it undergoes a ring cleavage. Forming, sorry, yes. Then forming this carbonyl system. Next one we will discuss, that is ozonolysis reaction. This is similar to that one, just instead of sodium tetra we are using ozone as our reagent. So ozonolysis is an organic reaction where unsaturated bonds are cleaved with ozone. Multiple carbon-carbon bonds are replaced by carbonyl group such as aldehyde, ketone and carboxylic acid. The reaction is predominantly applied to alkenes, but alkynes and azo compounds are also susceptible for this cleavage. So what will happen? So if you add ozone to this, just this shortcut to remember, you have to just cleave this double bond and just separate and add to oxygen. So just cleave this double bond and separate this part and add oxygen. You will get this. Separate this part, add oxygen, you will get this. Now this is now it has two types of condition. One is with zinc PPH3 or dimethyl sulfate, and one is along with H2O2. Now if you add, in case of aldehyde, if you give this condition, suppose if you gave the first condition, this one, if you give this condition here, what will happen? It will just cleave like this one and forming two molecules of carbonyl. One is aldehyde, another is ketone. Now but in presence of H2O2, that is in presence of oxidizing system, what will happen? This part will again take part in oxidation and forming acid. So in case of, if there is a possibility of formation of aldehyde and the ozonolysis is performing in presence of hydrogen peroxide, so instead of aldehyde we will get acid. But in case if the ozonolysis is performed in presence of some reducing agent like zinc dimethyl sulfide or PPS3, will just get the cleaved product, that is aldehyde and ketone. Now suppose if the reaction is performed in presence of NaPH4, that is in presence of reducing agent. In presence of reducing, what will happen? It will reduce this carbonyl system. It will reduce this carbonyl system to alcohol. It will reduce the carbonyl system to alcohol. So next named reaction we are going to discuss, that is Corey-Fuchs reaction. So this is a reaction designed to transform an aldehyde into an alkyne. So we have known in the last two reactions what we learned, how to get a aldehyde or ketone from a alkene. Now just go to reverse. How to get a alkyne from aldehyde? How to get a alkyne, not alkene. How to get a alkyne from aldehyde? That is the only reaction can be performed, that is a Corey-Fuchs reaction. So by suitable choice, we can even, there is possibility to stop this reaction at this place. Now suppose if we add this CBr4 and PPS3, what will form? It will undergo a Wittig type of reaction and forms this alkene. And if we add a butyl lithium, this is a negative source, this will attack to this bromine center. This comes here. So, sorry, not there. This will as it is a strong base and it can abstract proton. So, as it is so strong, it can abstract proton from sp2 carbon also. It will abstract proton from this position. This goes here and the bromine leaves from the system. We can stop the reaction at this place also. But if we add another molecule of butyl lithium, what will happen? That will attack at this bromine center, break this, and we know the sp carbanion are usually very stable, and if we add water it will get protonated. So this is it. So if we go into the mechanism, first this in the CBr PPS3 will attack to this bromine center, forming C minus, like similar to that Appel reaction, forming this C negative. After that, what will happen? This center, I am showing this because instead of the Appel reagent, whatever you used, if you use the same reagent instead of alcohol to a ketone, what will happen? So here the reagent is same, you can see. Here the reagent is same. Now if we add to a ketone system, it will attack to this ketone system, it will open up, and this O minus will again attack to this PPSC, forming this cyclic intermediate, and it undergoes a ring cleavage, forming this alkene. Now this alkene, again in presence of base, as I show, it get cleaved and forming this alkyne. Okay. So let's now focus on solving some questions based on whatever concept we discussed today. Just let's go one by one. I have just mixed up. Today we have discussed about substitution reactions and some double bond oxidation reaction and how to convert a aldehyde to a alkyne. We have discussed about that also. So just let's try to solve this. So if here they have given one compound, one substrate, and added this CH3OH, what will happen? You can see we have discussed about substitution, and this is a leaving group. So there is a high chance of substitution. So what will be the product? Okay. Most of you will think that product will be, this is 3 degree, so obviously there will be a generation of carbocation, and after that the leaving group will attack, the nucleophile will attack, and you will get this as our product, right? But this is wrong. This is not correct. So what will happen in this case, as this is 3 degree, but there is a chance of ring shifting. So this ring will shift here. Now this was 3 degree. This is also 2 degree. This is 2 degree plus 6 member, and we know 6 member are more stable. After that, there is possibility of methyl shift. So whenever there is a substitution, you have to think about ring bond shift. There will be methyl shift. To this place, then writing a carbocation here. So now this is 3 degree plus 6 member. So this is the most stable form. So the leaving nucleophile will attack and give us this as the product. Okay, understood? Let's go to the next one. What will happen here? This is also undergo a, whenever now the SN1 and SN2 type also depends on the nature of the nucleophile also. If it is a weak nucleophile, that usually prefers the SN1 reaction, because as the living nucleophile is weak, the substrate gets more time to cleave and forming the carbocation. But if the leaving group is, if the nucleophile is stronger, it won't give a substrate to cleave, it will attack faster rate. So therefore, whenever there is a water, whenever you can see a water or any neutral nucleophile, whenever usually you see in water or any neutral nucleophile, that usually prefers SN1. Now let's start. So this will leave from the system, generating a carbocation. The similar case, this will shift here. Generating a carbocation here. Now there is a hydrogen atom is there, so there is a possibility of hydrogen shift. generating this as our carbocation. So this is 3 degree as well as 5 member. So from here, if water attacks, we get this as our product. We get this as our product. Okay. Let's go to the next question. So what would be the major product formed in the following reaction? So what will happen? This Grignard will attack to this carbonyl system, forming this methyl. After that, when you add HCl, this OH will get protonated and leave from the system. Then the ring bond will shift. Further, like the previous one, H shift. Then our desired product will be this one. Cl minus is still in the system, still attack, and get this as our product. So if you see any reaction, if this product is given, how you can predict the retrosynthesis now? Now you can predict the retrosynthesis of the reaction. Which of the following is the major product for which of this? What will be the major product of this reaction? So what will happen? This will just attack here and it goes open, like similar to the previous one. Now in this case, what will be the product? So Cn minus is a strong nucleophile. Cn minus is a strong nucleophile. It will go to a SN2 type of reaction. So if we go through a SN2 type of reaction, yes, this is below the plane, so the product will be above the plane. Which is the major organic product of this reaction below? So you have to predict the major product formed in this reaction. Now you have to determine, this is a 1 degree carbon. So this is prone to perform a reaction through SN2 pathway. A reaction through SN2 pathway. It will go to a SN2 pathway, and if it is SN2, what will happen? That this will just substitute this bromine atom. So what will be the product? Option B. So just by seeing the nature of the carbon, you can determine which substitution will be performed. Next, which is the major organic product of this reaction below? So what will happen? So this is a carbonyl center and this is a Grignard salt. It is a delta negative charge. It will attack to this carbonyl center and this opens up and take proton form here. So which will be the correct option? Option B. Now next question. What will be the product of this reaction? No options are given. Just by seeing the reagent you have to understand which reactions is performing here. So what type of reagents you can see? You can see PPS3 and CBr4, and whenever there is a tetrabromide or tetrachloride and PPS3, that will be a which type of reaction? It will be a apple reaction. So let's start. I'm not forming the. So after all, like we have discussed in the mechanism, after all the attacks, what intermediate that is main required, I am just drawing that one. It will form this. Okay. So now if we react this one with this, what will form? It will form this. Now as O minus has removed this Br minus in the system, so Br minus is still there. Now this Br minus can attack to this substrate. Now there is two probability. One is this one is this one. From the experimental data, it has been seen that this bromine minus usually attacked to this position. This one of the double bond gets shifted and this gets removed from the system, generating an alene complex. Generating a alene complex. Okay, we just try to draw it properly. Okay, let's go to our next question. Now predict the retrosynthesis of this compound from this one. How would you predict? What will be the synthon or synthetic equivalent of this reaction? So what can we do? Now see, from this one you can see there one group here, this is below the plane, this is also below the plane. So this should be stick as its own stereochemistry. Now the incorporating group should be opposite to that this one. So when this is possible, if this is added to this one, then it is possible that it's incoming from the opposite plane of this one. So what is if we add NAVT, this will take up a proton from here. This goes here and forming this inlet anion. Followed by, you have to take this type of substrate. With the leaving group so that it can attack. So now this is, as this is below the plane, the incoming will be the above the plane. I'm not drawing it, I'm just going. Now you can see this is NO2 and this is NH2. What we can do, we just can add TAHCl. What will happen then? This TAHCl will lead to the reduction of this NO2 to NH2. This is selective to NO2 to H2, NH2. It will not reduce any with this functional group. Okay, it is selective to NO2 to NH2, TAHCl. TAHCl. So just if you know the different type of reaction, you can predict the retrosynthesis of any compound. Okay. Let's go to the next one. So what will be the product for this reaction among these four? So it's PPH3 and dead. So it is a which type of reaction? It is a Mitsunobu reaction. PPH3 dead means it's a Mitsunobu reaction. Okay, it is a Mitsunobu reaction. Now what will happen? So this will attack to this, PPH3 will attack to the dead first, then OH will attack to PPH3 forming this type of bond with PPH3 plus. Then after that this OH will attack to the nitrogen center and this leaves from the system. So what will be the our product? Product option A. It is easy because we just have to determine this OH will, in presence of PPH3 and dead, OH will become a good living group. In presence of PPH3 and dead, OH will just become a good living group. And if it is become a living group, then another nucleophile, the internal nucleophile, that is OH, will replace this from the system. So by PPH Mitsunobu reaction and Apple reaction, we are making a bad living group, that is hydroxyl, into a good living group. Okay. Let's go to our next question. So what they have added, let's go to step by step. First, they have added THCl, so it will become OTS. Now I'm just trying to draw it in open so that it give us easier to understand. Now they have added 4.5 equivalent of methyl lithium. So that means we are adding methyl lithium in excess amount. So suppose first equivalent of methyl lithium will added. What will happen? It will attack one of the chlorine center, and this forming a negative charge here. Okay, now this negative charge and release this OTS from the system. Now you can see this is how this is looking like. This is looking like a product of Corey-Fuchs reaction. Now you know there is another molecule of methyl iodide, 2 molecule of methyl iodide is there. So what will happen? First molecule of methyl iodide will remove Cl minus and generate a triple bond here. Second molecule of methyl iodide will remove another Cl. So what will be our product? Our product will be alkyne. Our product will be a terminal alkyne. Okay, understood? So this is the application of Corey-Fuchs reaction. So this much for today's class. So this is one of the homework I want to give. Just try this at home so that you will get an idea how to approach to a question. So thank you. I'll just give an overview of today's class. So today we discussed about different type of substitutions. First is SN1, then SN2. Then based on this named type of reactions, we discussed some important name reaction, that is Apple reaction and Mitsunobu reaction, and what is the advantage of these reactions. By these reactions we can make a bad living group, hydroxyl group, that is a bad living group which is not prone to remove from a system or get removed from a system. That OH group can be replaced very easily by turning it into a good living group. Next we discuss about these mechanisms and all. Then we discuss about oxidation of double bond. Two types of oxidation we discussed. One is this Johnson oxidation, second one is this ozonolysis. Then we discuss another type of reaction where we can form or generate an alkyne from aldehyde. Then we solved some questions based on that, which will give an idea. We also predicted the retrosynthesis of this compound and how we can apply our known reaction to a retrosynthetic reaction. Then we solve some two more questions. So this is the homework. Next class we will discuss some more reaction, like some extra we have discussed about the oxidation reaction, but there are some other left. So we will discuss some different type of oxidation reactions. So hope you will get an idea. So thank you for today's class. Have a nice day.